So we're going to keep going with our discussion about optimization and machine learning. Okay, so today here's the outline for what we're going to go over. We're going to first do a review of the spectral and mixing just to recalibrate everyone's mind. That'll lead us into this transition from optimization to machine learning. So there's just a few small changes we have to make to our mindset to apply what we just learned last lecture to achieve a machine learning approach. It's really pretty straightforward, but it's important to really understand those differences. Then I'm going to lay out all the ingredients we're going to need to execute machine learning. What is required to successfully achieve a trained ML model. And then we'll start getting into our very first example, which is a linear classifier. So this is like the simplest place you could start. And you'll see even that simple starting place leads to relatively complex mathematics. And so as you progress from that simple starting place, it becomes more and more challenging to write down equations and really track the whole entire pipeline. Okay, and so just as a reminder, last class we talked about spectral and mixing. This is the problem of effectively looking at a mix of colors and trying to distinguish what percentage of different colors that you put into the mixture are comprising that mixture. So the setup is shown here. We have some sample. I'm thinking of fluorophores used to stain some tissue or other biological material. But you can literally think of different types of paint mixing together to form a new blob of paint. The colors each have their own spectral signature, so that's a measure of intensity, right? How many photons per second is in each wavelength of the light from each dye, right? In this case, each fluorophore, each individual paint in the paint example. And you can measure those on a spectrometer, which is a one-dimensional array of pixels that returns a vector of values. So the setup for this is shown here. We have our input, which is our measurement of the spectra of some new sample, where it's some mixture that we don't know, right? That's the whole goal, is what percentage of each fluorophore is comprising that mixture. That goes through some model that gives us the output that we want. Here's the 9 percentages, right? Why 9? Well, we have to specify that at the beginning, right? So in these machine learning or optimization pipelines, it's really important to really define the dimensions up front. It's hard to create these platforms where the input dimensions and the output dimensions can change significantly. It's possible, but it just adds complexity. And so we set 9's fixed. And then remember the third ingredient of optimization, and an important ingredient of machine learning, is taking that output and seeing how well you did. That's a single scalar value that tracks your performance. It's achieved via a cost function. Okay, and so our problem, the spectral and mixing problem, we used an ansatz to assume it's a linear process that then allows us to describe the formation of, or our model rather in general, as a linear equation, x equals ay. A is this dictionary matrix that we talked about. Y then leads to a cost function assessment where we just said, hey, let's use mean squared error, because we assumed additive Gaussian noise, which, as we'll see, I think next class, is the mean squared error estimator is an optimal cost function to use. It's just, in general, a good one. The dictionary matrix looks like this. Right, each dictionary matrix column is just a spectral measurement from one of the colors independently, right? So that's something we have to create. That's knowledge we have to bring to the problem, right? We need to have that ahead of time. And so, this matrix vector product leads to a linear summation, a weighted summation rather, of the columns of this matrix A, which is each spectrum of each color, multiplied each respectively by the weight in its associated entry in the vector Y. All right, any questions about that setup? It's gonna be a very similar setup for our linear classification problem, so I just want to make sure this whole thing is clear. It's pretty straightforward. We then tried to figure out, well, how do we find an optimal output Y given this setup, right, this model, right? And so conceptually, this is what you have to kind of get used to thinking about. You have some model. You have something you measured or have, like an image, and then something you don't know, right, which is what you want. And so what you have to think about is the computer is going to twiddle what you want until it matches what you have, right? And those two things are connected via a model, right? And so in this example, the computer, we're going to kind of twiddle y, right, what we're trying to figure out, and you can project that through A to then make an estimated x, right, an estimate of the measurement, and compare it to what you actually measured. So you say, oh, let's just guess. Maybe all the fluorophores are equally represented. Each one's 11%. Let's go ahead and try that out, compare it to what we measured. It's off, right? Or maybe it's perfect, and then you got lucky. But generally it's off. Then you have to change the values of y a little bit, and then compare it again to x. And you always do that with your cost function. And so how good did you do is established by looking at the gradient, or the cost function rather, and then how to perturb it, how to twiddle it is established by the gradient of that cost function, right? Should I increase the first value or decrease it? Well, if I increase it, look, the cost function went up a little. If I decrease it, it goes down. So let's decrease it, right? That's the whole game. That's what we're going to be focusing on for this next class. And so a picture of that mathematically is really hard to obtain in these higher dimensions, but in these lower dimensions, you can draw this cost function. It's just a paraboloid, right? It's a squared difference. And the idea of evaluating the cost function is just you're at some point in this space, and then that point lies on the paraboloid somewhere, right? So you're going to guess a y, y1, y2, da-da-da-da, and then that has a particular value, f of y, on the paraboloid. And then its gradient is naturally just the slope of the gradient of the paraboloid at that point. And so it's kind of like this picture I showed before, where you're going down a valley, right? And you're trying to get to the bottom, because the bottom is where the cost function value is minimized. So to do that, we need to work with gradients, derivatives, right, in more than one dimension. And so we derive this gradient here for this cost function. You can then use that numerically, step by step, as we'll see later many times in this class, to take a step down the hill, so to speak, going down this cost function. So that's method one. Just do this numerically, which I'll return to in a second. We also saw in this example, you can kind of cheat, but you can, because it's an easy problem, just set the gradient to 0. Right, the gradient we derived. It's kind of like, x minus ay squared. You take the gradient, well, the squared goes away, but then the a needs to pop out through the chain rule. So that's the gradient. And set it to 0, and then you solve for it, right? And you just move things around. It's pretty simple. The A transpose goes through, and then you can't just divide by A transpose A, right? That's not how you do matrix math. You have to take it inverse and multiply it by A transpose A, then they cancel out. And so you have A transpose A inverse, A transpose X on the left-hand side, and that's equal to the optimized value Y star. Those first three matrix products, A transpose A inverse A transpose, we'll call W. Why? Well, it'll relate to what we do in machine learning in a second. We'll just call it W, okay? That's a pseudo-inverse matrix. Usually people write like A dagger, just so you know, but we're not going to do that. We'll call it W. And so you can kind of draw two pictures for this problem. One is what's called the forward model. So a forward problem is, hey, there's something that happens and then I make a measurement. It's like some physical process happens and that leads to what I measure, right? In physics, in chemistry, and biology. An inverse problem is the opposite of that. You have a measurement and then you want to undo that process. So it's like, hey, I measured this. Well, what's going on in the world, right? That's an inverse problem. Those are usually kind of hard to solve, right? That's the whole game in science. And so this is a forward problem that we originally wrote down, right? Because it's something's going on and causing our measurements. And then what I just described, having the measurement and somehow obtaining the percentages from that is the inverse problem, the solution to the inverse problem, right? So this linear equation, it's a linear problem. It has a relatively simple inverse solution, right? Y star equals WX. It's useful just to be aware of those two ways. You can flip it either way in this simple problem. And that's because, again, it's simple. We cannot do this in actual machine learning. This is what we did. We programmed this up in MATLAB, and we got this result, right? We said, hey, I'm going to solve for the optimizer just using this pseudo-inverse approach because I can. So that means I'm not going to do gradient descent. I'm not going to go down the hill. I'm just going to set the gradient to 0 and solve for that value y star. And so you get something that works great, and this is how you code it up. We get this result here. And then we had this kind of question. We were going through this process of examining these results, and they never really worked, right? And so a natural question is, and this is kind of an aside, even in this very simple problem, right, where everything is perfect, there's no real noise, and it's just a linear equation, we're still not getting a perfect answer here, right? I'm allowing the y's to be negative even, which isn't true, which we kind of went through last class. It still doesn't work, right? So why doesn't it work? In these types of problems, even if it's a linear problem, there's no guarantee of any solution, right? Unless certain conditions are met. It's very hard to get an exact solution, even in linear optimization. There's two general categories of issue you encounter. The first is when you have an underdetermined set of equations. So your matrix that's forming your linear problem generally has fewer rows than columns. It's also dependent on the structure of it, right? If it's rank deficient in linear algebra terms, you're not guaranteed to be able to obtain the solution, right? But here, it's pretty straightforward in this simple example. Let's say my matrix for the dictionary was 1, 1, 1, 1, 1, 1, 1, 1. Right? You can immediately see the problem there in trying to recover a solution. This means that each color emitted the same spectrum. Right, here's only 2 spectral measurements, but each column had a color, right, and then they're all the same. So it's very degenerate, people would say. It's completely degenerate, mathematically speaking, but also just intuitively. Each color you're mixing is the same, so how could you possibly tell the percentage of each one, right, if you tried to undo it? And so if you just write out an equation, let's say you say x is 1, 0, and y is ABC, and you compute ay equals x. You just get these equations. A plus b plus c equals 1, a plus b plus c equals 0. And there's an infinite number of solutions for a and b and c, right, for that problem. So there's no way to figure out what the answer is. So that's one scenario where you have an underdetermined set of equations. The second is when you have an overdetermined set of equations. And this is the situation we're in the previous problem. Overdetermined. So remember I was using this term hot dog and hamburger matrix. This one is a hot dog matrix, and then here we have a hamburger matrix. And so here's an example I just grabbed from Wikipedia, I think, of overdetermined set of equations. So here you have 2x plus y equals -1, negative 3x plus y equals -2, and negative x plus y equals 1, right? Those are, the resulting 3 equations from this matrix vector product or equation. And you can see they don't intersect anywhere. You just plot those lines. And so there is no solution in this overdetermined set of equations. And so you aren't guaranteed to find the answer in that case as well. And so generally pseudo-inverses are applied in this domain. And what a pseudo-inverse does is it minimizes the mean squared error of those 2 sides, right? And so it'll solve for the mean squared error solution. It'll effectively lie right at that intersection in between those 3 points. If you want to learn more about this, Gilbert Strang has great lectures online in the book, like 4 books, but the introductory book's a great place. Now I'm bringing this up because I want to emphasize that even if a machine learning problem is very simple, there's no mathematical guarantees, right? So we're really in a world of approximations. Right? You have to just get comfortable with that. Tractable approximations, though. We know how wrong we're going to be in these kind of approaches. In machine learning methods, we don't even have that luxury. Okay, so we had negative weights. We came up with these 2 solvers. We could say, hey, we have to constrain the problem. We can use a convex solver. And here's a secondary approach where we can say, hey, instead of applying a constraint on y, we can then change the equation and add a dummy variable, z squared, instead of y. And that will always be positive as well, or non-negative. And so then we can solve for z squared, and we'll get some potential valid solution as well. That didn't work, right? Because we went through the exercise of this being a quartic equation, right, to the fourth power, and those can wiggle 3 times. And so that means it can have, for each dimension, 3 locations of a critical point. And so if we have 9 dimensions, that's up to 27 critical points. And so if we went ahead and tried to go down the hill and end up in a valley, we'll probably end up in the wrong valley. Right? And so you can apply techniques to try and work around this issue by initializing many times and picking the solution that goes to the lowest mean squared error value. But, for 9 dimensions, that's doable, and under the assumption that your problem is quartic in complexity, but in nonlinear complexity. But that's not often the case. Usually it's even more complex. Okay. And so for those 2 techniques, we used gradient descent. And so gradient descent looks something like this. In that software under the hood, you set up the problem. You say, here's my equation. And then it'll immediately compute the derivative for you, or you assign it. In MinFunc, you have to assign it. In CVX, it computes it for you. In TensorFlow, it'll compute it for you. Don't worry. You don't have to write out a lot of gradients by hand. And then it initializes a guess. So it says, all right, let's give it a good guess. Often it's a random guess. Random tends to work great. So you'll end up somewhere on this paraboloid. You'll then evaluate the slope, right, the gradient. And then you'll take a step in that direction or proportionally towards that direction to go down. And then you reevaluate, see how you're doing, take another step, et cetera, et cetera. And so that's summarized by this equation down here, that at the ith iteration in this iterative going down the hill algorithm, you're going to be at a current location and then take a step in the direction of the gradient. And so here's the kind of critical transition. So in this problem that I just went through, again, we had a knowledge of this matrix A, which is the dictionary matrix. We also had knowledge of this inverse matrix, right, which defines the inverse problem W. And we know that firsthand, right? So when people do optimization, you know the problem setup as such. And those generally are like known from first principles, from physics, or from econometrics, or whatever discipline you're in. And then you're out to solve the answer, right? Find the best solution. And that's all you care about. In machine learning, the critical difference is you don't know that model. That's the problem we need to solve. So we don't know A or W, and we want to figure it out, right? We don't have kind of that physical or whatever situational intuition to establish a matrix or a nonlinear set of matrices that maps images of dogs to their correct category and images of cats to their correct category. I'm not able to write down a set of equations that do that. People have tried before machine learning, and I'm sure they failed. Otherwise, we'd be using those matrices. And so we need the computer to help us do that, right? And so what we do have in machine learning, right, if we didn't have anything, if that was it, then it's like, all right, well, we can't do anything. This is a really hard space to work in. In machine learning, you have a lot of data. So what we do have in our advantage, which is different than in optimization, is we have lots of different inputs. We don't just have one spectral measurement. We have like hundreds. And we also then have hundreds of example percentages, right? So we have data to help us establish a good model. And so we're going to go through that and unpack that. Any questions about that there? It's an important conceptual change we need to make from last class. You only care about finding this Y star in optimization. In machine learning, really what all of you are going to be struggling with on your homeworks and then for your final project is figuring out this model W. Once you get the model W, then you'll spend like 5 minutes figuring out Y star, the answer. But the real, 3 weeks plus of effort that you're going to be tearing, your hair out because things aren't working, is figuring out this part, this model. It's not going to be a linear equation, right? We'll go through that, and then you'll see it doesn't work. Here's our setup. This is what we need to change to our little flow up here. First, we need to figure out W. Right, so let's assume right now, for this class and next class, that we still have a linear model. Right, we still have some inputs, spectra or images, whatever it is, some outputs, Y, it's the percentages of fluorophores in the spectra or whatever you might want to think of, and they're connected via a linear equation, Y equals WX. Then we need to first figure out W. What is W? What connects those two vectors? So we need to use what's called a training data set to help us figure out this matrix W. This training data set will consist of many examples. Each example is a pair of vectors, an input and an associated output, right? So the vector that represents the measurement, right, or the image, or the spectral, right, values, and then the associated output, Y, for that's coupled with that measurement. All right, so the first step in machine learning is we're going to use that training data set to figure out W. To figure out W, we're also just going to use a loss function. There's many terms for this. People call it a cost function, people call it a loss function. I'll kind of say them interchangeably. I'll write L, and that stands for loss function. But people use the term cost function. Okay, so what's this loss function, and how's it going to work, right? And so we'll get into that. But really what this loss function is going to tell us is how good of a job are we doing figuring out our model W. That's step one, right? And so we can go ahead and guess a model W. We'll try out an input, X1, and it'll generate an output Y. And we'll say, hey, it made an output Y for a given model W. Does that Y match Y1? Because we know X1, when passed through the model, should equal Y1. If it doesn't, then we need to change our model W. How are we going to do that? Same thing, gradient descent. We're going to perturb the model a little bit, update its values, okay? But this training error, I'm writing in a very abstract form. It depends on, like I said, the output yi, the label yi, and then the output of the model f of xi and w. And so that's this process I just described. You'll input a example, spectrum, or image, right? Xi goes through the model. That equals f of xi comma w for a given w. You'll then compare that to the known correct label yi, mean squared error, or some other term that's summarized by this li function. Can take a lot of forms. And you'll do that for many examples. And then something you assume in machine learning is that every example you're going to try is equally important. And so you just sum up all of those losses to establish a total loss. Why do you assume every example is equally important? I don't know. But I rarely have encountered a scenario where you weight the different examples to be more or less important. You could. I just rarely see it. Okay, and so then what we're going to do is compute the gradient of the loss to update the model W, right, this matrix W. And so we're going to do that by computing the gradient of the loss with respect to W and going ahead and doing updates, right? And so that'll allow us to iteratively find an optimal model W that maps X's to Y's from our training data. We're going to do that. And let's say we're successful at that and we get a great model W. We still are not done. There's a couple more steps. So that's called training. That when people say training an algorithm, training a model, they're talking about those steps I just described. Then you have a model, you need to test it. You have to test it to prove to everyone, prove to the world that it actually works. Okay, and so testing consists of getting a new data set, a test data set. It cannot be the same as the training data set. If it is, then you're kind of cheating, which we'll talk about. And so you need to get a new data set to then feed those X's into the model. Now you're not changing W, it's fixed, and you just get an output Y, and you compare that output, or rather Y star, and you compare Y star to the known label Y. And you add up all the errors, and you check how well you did. And here I'm writing a mean squared error metric. And so this is really what we care about. that training process, whatever the loss that you get, all those values, they're not so important to tell everyone, tell the world, right? They just allow you to figure out a good model to use. And then it's really how well did it work, right? If it worked 100% of the time on new data that the algorithm's never seen, that's pretty promising, right? That could, go out into the real world and actually work, on new camera images or microscope images or whatever. If you do a really good job training and you find out a mapping from X's to Y's that works excellent 100% of the time on your training data, and then you go try it on your test data and it fails, well, that's no good. Doesn't matter how good you did on training, right? If it's just failing on all these new examples, it's not going to work in the real world, right? And so this is really the quantity that you need to report and be excited about or be dismayed about, depending on how high or low it is. So now we're going to get a little bit more concrete and actually start putting some values and stuff to these equations. So we're going to have this training data, and now let's talk about image classification. So now I'm writing a general equation. It's not a linear equation. It's F, can be any mapping that involves some transformation W in an abstract sense and inputs X to Y's. This process describes all of machine learning and artificial intelligence, really. You have inputs, you try to get outputs. There's a mapping between the two. Figure out the mapping. Once you figure out the mapping, then you apply it, right? So that's what everyone does. That's how they made DALL-E. That's how they made ChatGPT. That's how you can classify astronomy data, like anything, right? In finance world, I'm sure there's lots of inputs of numbers of stocks going up and down, and then outputs of what's going to happen in the future. And so this is very general. Now we're going to pick a very specific example, again, because of this course and what we're focused on, image classification. And so image classification, the X's are going to be images, and the Y's are going to be categories. What is the image? Out of a finite number of categories, what could it be of? Okay? And so we'll write our data sets like this. It's a set, right? So you use brackets, and that set contains two vectors, X and Y, and there's n members of that set, right? N meaning the number of training examples you have. So we need that to start. Here's one training data set we can use. We will use this on our homework. It's called MNIST. It's kind of like if you've Googled Intro to Machine Learning, it's what comes up. It's just a really nice, simple data set that's small. And it's images. There are a lot of them. I think there's 60,000 of these digits. Each one is a matrix. It's 28 by 28 pixels. Right, so it has 784 values as a vector. It is a flipped image, right, or inverted, I would say, in the sense that when people wrote these digits, the ink was black. So this is like what you would expect to see when people would write a digit, and the ink is black and the background's white. Generally, when I download them, for whatever reason, it's flipped. And I'm pretty sure when you download them, they'll be flipped. So this will be brighter and the background will be darker. So it doesn't really matter. Just be aware of that. I've had people confused by that in the past. You just kind of take 255 and subtract each matrix and you can flip it. So it's not a big deal. It's as if someone took a white pencil and wrote on black paper and they made the same thing. So to work with this, it's really hard mathematically to have these 784 long vectors following us around. And so to start, what we're going to do is take these digits and simplify them into a vector with 3 entries. Right? Then we're going to be able to visualize them. So we're going to start simple, and both in these lectures and the homework, we are going to take the images and then try to come up with one number that describes the total brightness of the image or the total intensity of the image. You might imagine summing up all the pixels would be a good way to do that, right? Something like that. And then a second number will describe their symmetry. How symmetric are they? And there you have a number of choices, right? Symmetric about which axis or whatever. You can imagine kind of drawing a line here and subtracting the right side from the left side and looking at the square difference. And that would give you an idea of symmetry along the vertical axis. So what's the third number? We'll get into that. That's going to be a constant. We're going to need a constant value to be able to describe these images as well. Or rather, we're going to need a constant offset in our model to be able to classify them. And so we're going to carry around a constant x0, right, just to help us with establishing an effective model that can not go through the origin of x1, x2 space. All right, and so if we have a three-dimensional x's, right, then our model, again, we're dealing with a linear classifier. It'll have 3 columns, right, because we're going to multiply a vector with 3 entries into the model W. And so to do that, it has to have 3 columns, and it can have any number of rows. Here, we're going to start with a binary classification problem, and so we'll just have 1 row, as I'll explain. The binary meaning, is it in this category or that category? Is it an 8 or a 2? Is it a whatever? There's other images we're going to work with, I think starting on homework 2 or 3. I forget. But these images here, we're going to work with are of cells. They're from patients, right? They're white blood cells. And you can see the little red blood cells around them. They're images that are centered on white blood cells, I would say. And they're captured from an oil immersion microscope that is an excellent system, used at the Duke Clinic a lot, like 200 times a day. And it captures per patient blood smear, like a few hundred images like this. It zooms and finds the white blood cells and then takes a little snapshot of them. These are 384 by 384 pixel images, a little bigger, and they have 3 color channels. So you have that third dimension, right? There's a red, green, and blue value for each pixel. And it's a lot of data as well, right? In mathematical space, right? There are a lot of dimensions, rather. So that's 440,000 dimensions just for the input space. So again, hard to draw pictures. But in our reduced dimensional space, right, intensity and symmetry, we can visualize things. So that's why we're working in there. So here is a picture of a bunch of handwritten digits that people wrote of the digit 1. And those then have been taken and their intensity has been computed. That's represented by the value along the x1 axis. And their symmetry has been computed. That's represented by the value on the x2 axis. And then it's plotted as a little blue circle. And then the same process is applied to the images of handwritten digits of 5. Right? And so those are the x's, red x's. And so you can immediately see, hey, in this space, those 2 types of digit form distinct clusters, right? They're not always totally identifiable as being of one cluster or another, right? Perhaps. But you can tell that, hey, if I were able to say, oh, let's kind of draw a line maybe right here or something, I would do a pretty good job of always being able to say, if the plotted value falls above that line, it's probably a 1. And if it's below, it's probably a 5, right? So that's what image classification is doing. Right? Specifically, in linear classification, it is a line. We are drawing a line because it's a linear classifier, right? So if we constrain our models to be of the form y equals wx, then we are, when we establish a w, figuring out what line in this space, it's really a plane generally, should I use to then draw a boundary between the 2 categories of data that I'm interested in, right? And so you can see it's not going to always succeed. It's actually going to not do a great job, as you'll see on your homework. And why is that, right? There's a 1 on this top left corner, which isn't even a 1, right? And so that's some error in either someone being stupid and not knowing how to write a 1, or maybe when they just input it, they input it 90 degrees rotated, right, into this data set, which is probably a grad student error. So I'm pretty sure a grad student curated this MNIST data set, right? I probably would guess the latter. But yeah, so there's an error, and this is always true. There's errors in your data, training data, that will always pop up. But yeah, the second insight you can probably make is that no matter what you do, there's no line you can draw that will ever separate these blue circles from these red X's and also these red X's from those blue circles, right? There's no way with a line. And so we'll get into that. We'll really think about that and dwell on that because that has to do with something called model complexity, which is something we have control over as we get into nonlinear models. But just be aware. Why did we have this like three-dimensional X thing, right? Well, let's look at that. So right here, there's 2 points, x1 and x2, but then we had this x0 value. And so in our setup, in our problem for this linear classification goal, we're going to set x0 to 1, right? And so every vector that represents this digit is going to be 1, its intensity, and its symmetry. And then we're going to always multiply that into our model, which is going to be a set of 3 weights. W0, W1, and W2. Why are we going to do that? Well, we always want this W0 because it's going to define some linear offset. And then we'll have a slope associated with x1 and x2. Right? It's not the standard like y equals ax plus b. It's like the a1 x1 plus a2 x2 plus c equals 0 type format that we're working with in this problem. And so they're both similar, but that extra variable is needed to get the offset that we want. Because otherwise, whenever we're trying to draw lines, and you'll see this on your homework, I think one of the questions is going to constrain you to not have that offset. The lines will always have to go through the origin, and then it's like never going to work, right? Because unless you're very lucky and you get some clustering where there's clusters down here and then up here, and you can go through the origin, your model's going to fail. Right up front, I'm going to show this, and this is something we're going to return to. Even before we do anything, right, you get your MNIST data. Even before you compute its intensities and symmetries, I would recommend the very first line in all my machine learning codes, apart from importing stuff, is to split my data into training data and test data, or rather to set aside my test data. So right up at the very beginning of everyone's code, I encourage you to just immediately, as soon as you can, once you've downloaded the data, set aside test data. Right? Why? Because that will prevent you from mistakenly mixing it into the training process. Right? Because when you evaluate how well did you do after you've gone ahead and figured out your model with the test data, you want it to be a true and fair evaluation on unseen data, as if that data came from somewhere else, new deployment of your device into the real world. Okay, so right up front, you split it up. And so how much should you set aside, right? That's up to you. Generally, something like 25% isn't a bad number. So just go ahead and take 25% of the MNIST digits and just put them aside, right? Okay? And when you're working with your own data, or be careful to make sure that's a random sampling. That test data is a random kind of subset. Not cherry-picked, like I'm going to train on all the good data from whatever experiment A and B and then test it on the bad data from experiment C or something like that. It's just a random selection is the best. It's the best place to start, I'd say. Okay, so we have our examples. Then we started making our model. We haven't really said what our loss function is. Okay, so let's take a look at the model and the loss function. So let's do a little derivation for general linear classification. What's a good model and loss function? Okay. So here we're kind of taking a step back and saying, all right, we have a classification problem which can have 5 or 10 categories, right? Or some number of categories. And so we're going to get to this not for binary classification, but let's say you were actually trying to classify all of the handwritten digits. Which one's a 0, which one's a 1, which one's a 2, up to 9, right? So then in a general classification problem, linear classification problem, you'll have the number of categories is the number of rows in your W matrix. And then, the input dimension will define the number of columns. Okay, so that's just a general form. That's useful to know. We're going to boil that down to binary classification, right? And so we're going to say, we're just going to reduce the output to a single variable. And then we're going to, as you'll see, look at the sign of that variable. If it's positive, it's going to be in category A, and then if it's negative, it'll be in category B. Right? But this is just, again, kind of taking a very general equation which describes any machine learning AI problem, assuming it's linear, which automatically disqualifies us currently from doing anything useful today. You can't do any useful machine learning by having this linear, but for mathematical, whatever insight, we're going to do that. And then we're going even one step further and saying, okay, now we're reducing our attention just to binary classification problems. And then we get a relatively simple form, especially when we say, all right, our loss function is going to be mean squared error. That takes us one more line further down. And so now our loss function is just the sum of the inner product of some weights W times the input, right, image, quote unquote, X, where it's been summarized as a vector. And we then compare that inner product. That's going to produce a categorization, right, Y star, that we're going to compare to the label YI via a distance, right, a mean squared error measure. So we're going to sum up all of those distances between the predicted categories and their actual, and that will give us a measure of how well our model W did at drawing a boundary between these two. That's L, the loss. Okay, and so what's this thing going on at the bottom? Well, this is this little trick that we're going to use to make this problem result in a scalar value. Like I said, a single value out there. To actually establish a category, we need to take whatever's happening and make a final decision, right? In classification, it's all about deciding, right? Is it category A or category B? And so mathematically speaking, to decide, we're going to use this sign operator. The sign, generally, if the input to the sign operator is less than 0, the output's -1, right? That means it's cast to be a value -1, which is associated with category A. And then if it's greater than 0, it's cast to be +1, which is category B, right? So like if the input X of sign is 100, it's +1. The input X is 0.1, it's +1. Right? The input to the sign operator X is -1,000,000, it's -1. It's -0.00001, it's still -1. So that's its job, and that will allow us to kind of really say, yes, this is in category A or in category B, and then compare that to the known label. The known labels, YI, will be of the same form. They'll also be +1 or -1. +1 if it's the handwritten digit 1, and -1 if it's the handwritten digit 5, right? In the plot I just showed of the 1s and 5s. So we're going to need to construct all of that in Python on our homework. All right, and so what does this look like? So I tried to draw this out because it's a little bit confusing. And so I did my best to actually draw what's happening here. Because if you look here, before we apply this categorization type operator, this should look familiar. You've probably seen something like this at some point in your math studies, right? It's such a kind of common equation. Usually that type of equation is found when you're doing regression, linear regression, right? It's saying, all right, I have a bunch of points. I want to fit a line or a plane to them. And so in the past, I've had a number of confusions or questions about, hey, this looks like a regression problem. How's this classification? Like, what's going on there? Okay, and so these following slides, I'm going to try to draw that difference. And it's confusing. I'm going to preface this. And so if you're confused and you keep saying, why is this a regression and not classification or vice versa, go back and look through these slides because they will, I think, elucidate this. So with this equation, right, if you've done linear regression before, you have a plane that's defined by the vector W, right? Just like the slope, y equals ax plus b, the value of a and b. right, is summarized by this vector w, which in more than one dimension becomes w1x1 plus w2x2, et cetera, et cetera. Here we have 2 dimensions, x1 and x2. And then you're comparing that to some value of the function y, right? And so I'm drawing y on the third axis, right? So just abstractly, if this was a 2-dimensional problem, I think this would be even clearer. You'd have like the loss equals the sum of the square difference of ax minus y, right? And so you have points of form x, y, right, y on the, and so you're just trying to figure out a slope, a, that best goes through those points. Right? And so that's what I'm kind of drawing here. Without any categories, you try to find a w that minimizes this equation, right? It minimizes the squared error, which means it minimizes the distance to all those points effectively. You're going to find a plane of best fit for these points. That is true, right? And so, but this is abstracting away the value of y as just some arbitrary value. In classification, y has only 2 values, right? It's only of 2 categories. And so the y's in this plot are going to either exist at +1 or -1, right? So see how I made all the dots go up or down, right? And so this is more of the form of a classification problem. So you're still trying to find this plane, and that's still possible. But really what you're interested in, because we're applying this sign operator, is the intersection of this plane of best fit with the y=0 axis, right? Because what we're really trying to figure out is when does the value that w transpose x form, when is that inner product going to be greater than 0 or less than 0, right? So w transpose x lies on this plane, and when you say, hey, is it bigger than 0? You're looking at the values above this y=0 plane, and when you're saying, hey, is it less than 0? You're looking at the values below this y=0. So really what ends up being important is the intersection of this green plane and that y=0 axis, right? So you still are solving for this plane of best fit in this 3-dimensional space, right, where y is the third axis when you do classification. But it really boils down to a 2-dimensional problem where you're after the intersection of the plane you're solving for, w, and this y=0 plane, which is this dashed line, right, which I'm just drawing as an intersection line. And so usually when I was plotting those 1s and 5s, right, we don't plot a 3-dimensional plot, right, where y is an additional axis. We were just drawing dots with colors, right, the blue circles and the red X's, right? And so what's happening is you're projecting these dots down, you're removing the y-axis, and you have your points drawn as colors, and the boundary you're establishing in this projected space is this line that is the intersection of your plane of best fit and the y=0 axis. Okay? So I know that's a little confusing. I do that because usually each class I get later on a number of questions. Hey, like, isn't this linear regression? This is so similar to what I'm doing in my statistics class. And the answer is it is. But you have these values that are categorized on one axis, and you're still trying to fit them, and then that fit is only important at the intersection of itself with a particular axis. And so you remove one dimension from your normal regression analysis and just think of it as categories. Okay. And so what happens when you go ahead and try to perform linear regression, you guys are going to create plots like this in your homework, is you'll get results like this, where it doesn't work well, in short, right? And so here, there's many procedures to try to improve on this, right? Obviously, this has been around for a long time, this type of approach. And we'll walk through all the ways we can do better from this very simple starting point. But at least we can write down kind of closed form equations that describe this and draw pictures and stuff. So we've got a model and a loss function checked. All right, so now what's the third thing we need in machine learning, right? We have our training data. We went through what that is. We have our model. I'm writing the sign of W transpose X. And now we need to figure out the weights, right? And so how do we go ahead and optimize those W's, right? Well, we're going to perform gradient descent, right? Just like before. In this simple problem, we have the luxury of also using a pseudo-inverse, right? Because it's a linear equation. So that's the easiest. In general, in other problems in machine learning, you cannot do that. We'll try that on the homework. There's several different types of gradient descent, and one of them we'll also try in the homework, something called numerical gradient descent. So that's it for this class. I don't want to get too much in the details about these three approaches to solve for the weights, but we're going to try each. And you'll see they'll each work differently, right? And so even for a very simple problem where everything's linear and, you think there's equal signs and we'll get the right answer all the time, we won't. And it really depends on our methodologies that we adopt. And our different methodologies, as you'll see, some will be really fast, like take less than a second. Some, like this one, will take an hour sometimes to compute. And then this one's pretty fast too. So it's all about practicality, right? It's all these other factors we need to consider.